Thanks, Tracy.
You can
All right.
go ahead.
Thanks for the introduction. My name is Josiah Strauss. I'm with Neptronic. So we're a manufacturer of controls, actuators, humidifiers, electric heaters. Let's make sure I can. All right, there we go. We are based in Montreal, in Quebec. We've got close to 400 employees. We've got one large manufacturing building in Montreal. We actually just purchased another one. So we're expanding in the last, you know, 5 years pretty rapidly. And we're expanding our product line as well. So our office locations, I'm actually based out of Colorado. I'm in Denver area to handle US sales. But we do have some other offices around the country and around the globe. And we really have a fully integrated factory. So we always welcome guests. It's integrated in the fact that we, really capture the complete manufacturing process. So we're doing all our own sheet metal. All our cabinets are made in-house for our humidifiers, our electric heaters. Everything's fabricated in-house, and that also goes for software as well. So we write all our own software. We do all our own PCBs. We have multiple SMT, surface mount lines. It's really, and we squeeze a lot of that into our building. We do, we are actually through COVID, put a lot more emphasis into automation, and it's really improved our lead times and our ability to fabricate the variety of products that we make. So like I said, our main product line that you're probably familiar with would be humidifiers, but we also have electric duct heaters and compact makeup air, which I'll just spend a second on our duct heaters. We do open coil or tubular fin tube heaters. They're all custom built and selected in our selection software. So they're all selected to size and to kilowatts. They're not really a packaged item unless you would consider our fresh air zone heaters. We also make all our own controls for our electric heaters or humidifiers as well. So it pairs up very nicely. And these are good for, a kilowatt up to 1000 kW. So we can build very large heaters for like large air handler applications, industrial applications as well. There's really no limit. And we also have a compact makeup air unit that's been getting a lot of becoming, we're selling more and more. It's becoming more popular. And now that's available at up to 2000 CFM of makeup air and up to 35 kilowatts of heat. So right now we're just doing heating. We don't do cooling, but we do have options coming right down the road for like evaporative cooling that's going to go into the makeup air, as well as like ERV, like a heat exchanger. That's going to make it just that much more efficient. So if you have any questions about that, just get in touch with Tracy or whomever you talk to at Holden. And we also have a selection software that's pretty sophisticated for our heaters, our humidifiers, and makeup air and evaporative coolers. So this is something that's not limited to our reps. Engineers can have access to it and design, heaters or humidifiers or projects and get all their submittal information and documentation, without on their own. It works pretty well, and you can get in contact with Holden to set up a login if you want to play around. It's a good sandboxing tool as well if you just want to take a look at humidifier load calcs and stuff like that. I just where are our products? We have them in a variety of different high profile places. It really runs the gamut on applications. So we have a lot of aerospace, a lot of museums. So we've got humidifiers in the Louvre. We've got them in SpaceX and Tesla, the Pentagon. There's really, a lot of different projects. Generally, they're high profile because that's where you need humidifiers and typically critical spaces or, for manufacturing or healthcare. And so as a result, we're in a lot of hospitals as well. So why that brings the question, why do we humidify? What are we trying to accomplish with humidification, and why is it necessary in the built environment? And really, this is just basic stuff. The earth is 70% water. We're almost nearly all water in our bodies. And so, we, from a health perspective, moisture's good, not too much, obviously, but it's good to have in the air. So there's a whole air quality component to this. And then that's exacerbated by the fact that cold air, even though it may be 100% relative humidity, it's still not holding a lot of moisture. So when you heat it up, you dry out the air pretty significantly. And that's all. We can look at that on a psych chart. We will look at that in a few minutes. And the idea there is in a lot of climates that in the winter, when we're heating, we're needing to humidify to add moisture to the air to make it comfortable. And so that's why indoor air quality is a big application for humidifiers. So hospitals, healthcare applications, workplaces to a degree may use humidifiers. I know we're doing a lot of work with tech firms that are putting humidifiers into building spaces into workspaces and administration buildings, because it's making people work more efficiently and be more happy in their office. Schools, not so much in the US, but more so in Canada. We see humidifiers in schools. It's kind of an expensive to put humidifiers in classrooms. Residences, it depends on where you're living. I see a lot of them here in the mountains, in the Northeast, Chicago, Milwaukee, those kind of cities, and airports occasionally, or public spaces, train stations, that kind of thing. The reason why we see a little bit more focus on public spaces is because it's part of indoor air quality. It improves overall health. So if you look at, this is the Stirling plot, it shows basically where relative humidity can range and improve or limit things that can affect our health, like viruses, bacteria, ozone production, respiratory infections in general. And it shows if we keep a indoor relative humidity between 30 and 60%, that will mitigate those risks. So it's a public health issue as well. And there's a lot of work previously on the flu, influenza, and transmission of flu, where humidified spaces reduced transmission. There's two kind of pathways to this. One is when you humidify an indoor space, the viruses can't float around in the air basically as much, and they don't spread as much. And it also has to do with our respiratory systems, and that when our respiratory system is stressed by warm, dry air, the mucus that moves the particles that we're breathing in off our surfaces of our lungs and our respiratory system, well, that dries out as well. So you get you're basically extra susceptible to there's extra risk to getting the flu or COVID in this case. And there's a lot of data on this. It's all published online that you can just Google, and Google Scholar will pull up a ton of articles on looking at humidification and improving, and as a component of indoor air quality to fight viral diseases like the flu or COVID. So what about other applications beyond indoor air quality? Well, we can look at paint booths. That's a big one. So anything from painting like a car part like a steering wheel, or a iPhone, a glossy surface like that, to um, painting, a rocket or something like that. You will need a paint booth for that, and that humidity control can be an important part of that process, because it's just the way the paint adheres to the surfaces is influenced by the relative humidity. You want it to dry right. So pharmaceutical, same thing. You want to maintain relative humidity, and with compounding pharmacies, for example. So semiconductor is another, application. So if you're making processors, you're going to want to control your indoor relative humidity, prevent static. And then, so these are all process and manufacturing applications. Laboratories is another important application for humidifiers, especially with high-tech equipment, mass spectrometers, NMR. They require humidifiers because you want to make sure your environment is stable. Microbalances would be another thing. If your humidity is fluctuating, your weights of materials are going to change. Your balance is going to go out of spec. So it's really important for keeping equipment in spec. Another thing is for material integrity. So this could be, like artwork would be a good example. So any kind of museums that, have artwork, or, artifacts, or, priceless things, they're going to probably require humidification. Artwork's a big one because it's usually insured, and the insurance will require humidification or good environmental control. Similar with, actually, this is a good example. In schools in the US, you'll see one humidifier. It's always in the music room to preserve the instruments. So if you have like a guitar at home, you might even have a little, humidifier that you stick on your guitar that keeps it humidified in a case. Well, if you have a lot of instruments, you'll humidify the space. Similarly, for textiles, some of this moves into the more industrial, wood storage, textiles. You're probably just spraying some mist into the space, but you want to, keep the environment pretty stable. And then a growing application is data centers. So this is something we're seeing, as it has expanded in the last 10 years, exponentially. So this is actually a really good case for adiabatic humidification, because you have so much heat generated from the data center equipment. You can use humidifier to you can evaporate the water with that heat and get free cooling, basically. Occasionally they'll use steam humidifiers as well. Depends on the size, depends on the type of data center. Whether it's a leased data center where they have different data halls for different customers, they're going to have a different approach as a giant Microsoft or Meta data center. So it's going to kind of depend on the design. It's also going to depend on where the data center is. If it's in the Southwest and they have access to a lot of water, they're going to probably use some kind of evaporative cooling, and do humidification that way. So, what's the target relative humidity for all of these applications? It kind of fits into about 30 to 50% relative humidity. And that's really what the building envelope can maintain. It's what's achievable, and it's what's beneficial. You don't want to have a building at 60% or 70% relative humidity, and you're going to be condensing on every cold surface. You're going to condense on the windows, and there's no real point to that. So typically targets are somewhere between 20 to 50%, I'd say a lot of the examples here have 35, but for hospitals, I think ASHRAE will say 20% is okay. And for that, you still need humidifiers to keep 20%, especially in places like North Dakota, or Edmonton or something like that, where it's really cold and pretty dry. So we're doing humidification through two different types of humidifiers. You may see isothermal and adiabatic. I'm going to throw those terms a lot around in this webinar. But with isothermal, we're basically adding moisture without changing the temperature of the air. So basically, we're doing that by boiling the water with an outside energy source, electricity, gas, and steam, pressurized steam, and adding that to the air. There is some minor change in temperature, like a sensible heat gain from the manifolds that provide the steam to the ductwork, but it's not a significant factor. And so if we look on the psych chart on the left, we see the isothermal humidification line. That's the one that's going straight up and down. Maybe I can do annotation. So in this case, we're starting off at this point here, and at 75 degrees. That's a little warm. Maybe this is, and we're moving up from a point of 26% to 60%. So maybe this is some kind of process application where they need a little bit of higher relative humidity. And what you're doing here is adding steam, and that's just raising your relative humidity. Now, what we're going to focus more on is the adiabatic side of humidification, and that is basically adding moisture through the air and allowing the air to evaporate it, and that's going to give you the cooling effect. So it's going to, bring you out here. So your dry bulb temperature and now is going to be 60 degrees. You've added moisture. You're getting to about 60% relative humidity, but you've dropped your air temperature. And that can be a huge advantage depending on the application, or it could be, not much of a benefit. So if you had a hospital or something like that in the winter where you're going to be in heating, it might not be a big advantage, but it's going to be essentially the same physics, the same net energy consumption to do either one. You're either going to apply electricity to the humidifier, or you're going to apply electricity or gas or something to preheat and evaporate the water off of a media, or evaporate mist, basically. I have to turn off it. This is always where I get stuck. There we go. So just kind of gives you an idea of the energy consumption. And so if you're always in heating, there's no really net benefit to going with an adiabatic humidifier if your humidification coincides with your heating, because you're just going to have to heat more to evaporate the water. And what that's going to just create, it would be probably easier to control using steam, just because it's the humidifiers are more versatile, easy to install, and you don't have to worry about preheat. However, if you're in cooling when you're humidifying, or you're in the shoulder months, you blend basically these two, the adiabatic cooling with a preheat, and you do get some overall net energy savings by doing an adiabatic humidifier. So depending on the application and depending on the climate, it's a more efficient way to humidify. In the worst case scenario, it's going to have the same energy footprint. You're just going to have to, the controls are going to be a little more difficult with adiabatic, and there's some microbial risk that's generally made this not as attractive. But considering we're looking at more efficient buildings now, it's becoming more popular. So overall, I'll just go over the types of humidifiers we have that are isothermal and adiabatic. I'm not going to go in detail, but I just wanted to make sure we're all aware. So for isothermal humidifiers, I'm talking about electric. Those are good up to 100 kilowatts, and that's pretty much across brands or manufacturers. And that would make up to 300 pounds per hour. Going into a larger humidifier would be gas fired. And so then you're into your 500, 600, 700, 800 pounds per hour. For a gas humidifier, steam to steam would be using boiler steam to make clean steam humidifier. And those can get rather large depending on the pressure of the steam you're putting into the heat exchanger. Those can get up to 1,200 pounds per hour. Direct steam, you're just putting boiler steam directly into the air handler or duct, and you're getting, could be small capacity, 5-10 pounds per hour, up to very large, 12, 13, 1,400 pounds per hour. It all depends on the size of the valve and the amount of steam that you're putting into the manifold. And then we have adiabatic humidifiers. Really, the largest capacity humidifiers are going to be the atomizing, one on the lower right. That's going to be a high pressure spray, and that you can go up to about 3,000 pounds per hour. We have evaporative. That's going to be a media, and really the load kind of depends on. It's going to be can be several hundred pounds per hour. It depends on the size of the media, the thickness of the media, and your air temperature that's entering the media. So this just gives you an idea of what we manufacture and that we have to work with for humidification projects. And then adiabatic humidifiers. There's one we don't make. That's actually an ultrasonic humidifier. This is kind of a specialty humidifier. You actually see this in a lot of homes. It'll make like a mist that's basically created using it's almost like a speaker that vibrates under the water at a certain frequency. And then you have, you're creating very, very small water droplets. And then that's pushed out of the the chamber. And you'll see these go, they're typically used in small server rooms, computer room, air conditioning, server rooms, those kind of applications. They're limited on capacity, and the higher the capacity, the more maintenance you have to do, because the sort of speakers, the vibrational plates can only be so large, and so you're just really having to change a lot of those at higher frequencies. And the big benefit here is that they create a mist. They do have evaporative cooling. So for a data center, it would work out pretty well. The only issue here is that you need RO water, because if you don't, you will get dust on all your surfaces from the minerals that are in the water. That could be really problematic in a data center if you don't use RO water. And then your limited capacity and added service. But they do exist. Stultz is probably one of the most popular manufacturers. High pressure spray is the one we're seeing the most increase in demand over, and that's because it's really versatile for an adiabatic humidifier. You can put it in an air handler. You can put it directly in space, and you're evaporating. You're creating a very fine mist using water that's under pressure. And when I mention pressure, it's 1,000 psi is typically what we run at, and the loads can be highly variable. So we can go down to pretty low capacities. We can have this with a VFD on the pump and get a low output, or we can go all the way up to in this case 2,800 pounds per hour and have a really high output. So the turn down ability is pretty good on these, especially for an adiabatic humidifier. The other thing is the service is going to be at a fairly easy on the humidifier. It's basically service on a pump, but the installation itself doesn't really have to be touched. Then if you do have a nozzle that fails, it's something you just pop out and replace. It's not very difficult. There's no cleaning involved um, with the unit, and the units are really good for uh, shutting down at the end of the season. So you could run at lower pressure with a drain open and really flush the lines, get water out of there. They're not going to have standing water. And that's what really sets them apart from other adiabatic humidifiers, like evaporative media. So evaporative media, you can either have a single pass system or you have a basin that sits with water that keeps passing over the media. But why these were typically avoided, especially in healthcare, which I'll have another slide on that in a second, is that they were, you had standing water basically in the air handler or the other duct. And that's why the high pressure doesn't do that. So it's generally more favored. The big benefit, though, to evaporative media is that you don't have to use water treatment. So you can run any water over that media, and you're not going to have to, treat it. And the media itself is relatively inexpensive, so service is also really easy. So the big benefits to media would be no water treatment, easy service, so it's generally low cost and efficient. And so the media really has its applications that it's oriented towards, especially data centers, because here you're not, you're evaporating the water, but the anything that's in the water, dissolved minerals, are going to stick stay on the media, so you don't have to worry about that, and you don't have to treat the water. So water treatment can be wasteful. So this is a more efficient way to go about that. So overall applications that favor adiabatic humidifiers, those with high capacity needs, so 1,000 pounds per hour plus, they're either going to have multiple isothermal humidifiers, or then you can use one adiabatic humidifier and go about it that way. So makes sense there. Anything where you can take advantage of adiabatic cooling, so depending on your climate, that's going to make a lot of sense. Or if you have some kind of heat generated in the space, where you can use adiabatic cooling, like a data center or some kind of industrial application, large printing space. There's going to be a lot of equipment in there, and you'll get something out of the cooling. Paint booths, again, that's tied to capacity. Dust collection, and then there's other applications that we don't even think about. Concrete curing. So if you get a new concrete driveway, you got to spray it down with water for a week. Same process. There you want to make sure the concrete cures correctly. Greenhouses, grow facilities. So industrial grow facilities. We have quite a few of them in Canada. They use high pressure spray for either drying whatever you're growing or cultivating whatever you're growing. Healthcare has traditionally been a place that's avoided adiabatic humidifiers, namely because of Legionella risk. So you can look up, there was an outbreak in New York. There's one, they happen in Europe fairly often, because Europe doesn't have the power grid to use isothermal humidifiers as much as the North America. So you'll see occasionally there'll be outbreaks of Legionella. And basically what it is gets in a moist area in the building. So you have a microbial, like little microbes, these Legionella bacteria that will, reproduce and get in your respiratory system, and they give you like a pneumonia type sickness. And in hospital and healthcare applications, it's been avoided to use adiabatic because it can contribute to this. If it's not properly taken care of, if you had a evaporative media that sat up out of someone's maintenance, or just sat in an air handler and was broken, or some valve was broken on it and it just kept flushing water, or it didn't drain correctly, or the drain was blocked, you'd have an issue where this could be a possibility. So traditionally, that's been avoided for healthcare applications in favor of hot steam isothermal humidifiers. However, that's changed. And now, since ASHRAE added some rules for standard 170, that has to do with ventilation requirements and healthcare applications. And now they're basically allowing high pressure spray to operate, to humidify in hospitals. And so what this means is that the push here is for energy efficiency, decarbonization, and it really helps with, if you have a large hospital, traditionally what we would do is put humidifiers in the air handlers and then have some spot humidifiers in the operating rooms to make sure those are at a little bit higher relative humidity. In this case, the air handlers, they have a large capacity, right? You're talking about at least, maybe at least several hundred to several thousand pounds per hour, depending on the type of hospital, whether it's, a small regional or a big, large hospital. And so that can be more easily accomplished with a high pressure spray humidifier. And the reason why they're not choosing any of the evaporative media there is because the high pressure spray, you just have more controls on the hygiene. So you can, turn it off. It's you're not going to have wet media or standing water in the air handler, and you can have more protections. You can do UV light. There's RO water treatment, so you can eliminate the potential for a lot of the microbes. And some states mandate this too. So California Title 24 mandates that adiabatic humidifiers be used in place of electric or steam isothermal humidifiers for a lot of applications, mainly data centers. So you can't use a steam humidifier in a data center. It has to be adiabatic. And then a lot of municipalities, this not just California, are getting rid of gas. So that's a huge push that we see going towards high pressure spray, and is because the elimination of gas really eliminates the high capacity humidifier that can be put in an air handler. And if you have a load of 2,000 pounds per hour, you could have accomplished that with several gas humidifiers. If you had to do that with electric and go with electrification, you'd have, half a dozen humidifiers on there, and it would be a lot of maintenance. It's going to be, more equipment, more space, more installation. You might as well just put a high pressure spray, and then either if you need preheat, you could put in, a larger coil to handle that upstream of the humidifier. So it's starting to make sense for a lot of larger, building spaces with the elimination of natural gas. So I talk a lot about a high pressure spray. You do need water treatment for that. And the only thing that really will work for high pressure spray is reverse osmosis. This is because you need the water treatment to, one, eliminate your nozzles, your spray nozzles from being clogged, and then two, to eliminate dust that's going to, or particulate that's going to be left over when that water evaporates. So you can look at nanofiltration, can get rid of some ions, but really reverse osmosis is the way to go. Reverse osmosis skids are typically paired with high pressure spray humidifiers, and they're also paired with ultrasonic, and they really are can vary in capacity and are kind of tailored to the humidifier itself. And so we do provide these as well with our humidifiers, and they're really also, they can be used for isothermal humidifiers as well to remove maintenance. So they're good on that side as well. So they really serve multiple purposes and are a great ancillary tool for humidifiers. And so basically just a little bit on RO is that it's not just one RO, a single RO system. You have, it's a water treatment system. RO is part of that. So you will have a pre-filter, something to get rid of particulates in the water. You'll have a softener, in most cases, to pre-treat the water so it's ready for RO. You'll have an RO system, some kind of storage tank to store the water and to distribute it to the humidifiers, whether it's spray or isothermal. The reason for the storage tank is you do need a buffer in between that kind of acts to supply water before the RO can start producing, or if the humidifier is using more GPM than the RO is capable of producing at a given time, and the RO then can catch up later. All right, so load calcs. These are the same for isothermal and adiabatic. Really, we're looking at how much ventilation and what are the outdoor conditions that are going into the space. So ventilation adds the need for humidification. The more air changes, the more you're going to need humidification. And ventilation is something that, air changes are something that we're probably going to see go up. There's a little bit, was that an ASHRAE talk not too long ago, and we're talking about the number of air changes in a hospital, a school, just to improve the or limit exposure to improve public health, limit diseases or sickness. You're going to see more air changes needed in certain spaces. That does make an impact on humidification. For some adiabatic humidification, that's not a big deal. It doesn't really create much of an energy demand, but for isothermal, it definitely will, and depending on where you are. But we're going to need to know how much outside air is coming in, what's the design condition of the space, and then you can look at your distribution and select that. Whether for a adiabatic humidifier, it's either going to be in the air handler, in a duct, in space, like either with a media with a fan or with high pressure spray nozzles. So just doing the psychrometrics of here we have outside air. This is an easy one because we get mixed air conditions. So this is a paint booth. You're bringing in all outside air. So that's why I'm on. It's the easy approach. So basically, we want to get to where the supply air is, the red X. So with isothermal, the pretreatment, or sorry, the preheat temperature is just the sensible heat that you want to, the dry bulb temperature that you want to raise it. So from 10 degrees to 70, you got this, or basically 60 degrees of temperature change. To do it with adiabatic humidification, you'd have to heat the temperature all the way up to 115, thereabouts, and then add the moisture. So here it's a wash as far as efficiency. You're not really getting any efficiency. The energy consumption is going to be approximately the same for isothermal or adiabatic, but if you're only doing it, running this during the winter, you're probably go with an isothermal humidifier for this application. And then this is just the math to get your load calc. So we have software, like I mentioned before, it's going to get all our load calcs done very easily. And it can also do adiabatic humidifiers as well as isothermal. The one thing you are going to have to consider is, in addition to your ventilation in the space, what about leakage? If you're economizing, whether that's going to work in favor with adiabatic humidification or with isothermal, you may have to lock out economizing because you don't want to be using 50 kW or something to make a bunch of steam just to not run your cooling or your coil, or it could be energy inefficient. So that's something to take into consideration. And you can also look at distribution in our software as well. So one of the things, and independent of type of humidifier used, is if you are humidifying a building space, this would be like a operating room or a laboratory or some kind of space within a building and you're not humidifying the rest of the building, it represents some unique challenges. So you want to make sure you isolate the space with vapor barriers. You want to make sure there's, the door entries are sealed because moisture will escape. You want to make sure it's on a dedicated AHU. Otherwise, you're going to be humidifying the rest of the building, as your moisture is leaving through the return air. And you want a positive pressure, have the space under positive pressure. And temperature is integral to controlling relative humidity because it's relative to temperature. So an improperly placed humidistat could create issues. So that's more of an install thing, but it's definitely has an impact on high pressure spray and adiabatic humidification because we're dealing with not just adding steam, where we're not changing the temperature, but if you're adding moisture and you have a 15 to 20 degree temperature drop after that moisture is added, you either have to have the preheat under control with the humidifier, or you're just going to be spraying water down the drain, trying to keep up with a demand from the space humidity when you're trying to humidify. So that can be a risk with installing adiabatic humidifiers in like air handlers, where you will have demand for moisture, but really there's no thermodynamically, there's no room for it in the air that's going through the air handler. So it just goes down the drain. All right, so that was kind of an overview of adiabatic humidifiers, applications. I'll talk a little bit about our products now and what we have, what we manufacture for adiabatic humidifiers. And if you have questions on isothermal, we can set that up for another time. So we have our SKH4. It's a high pressure adiabatic humidifier. So this is going from 100 pounds per hour or less, or 50 pounds per hour. So small capacities all the way up to 2,800 pounds per hour off a single pump station. I was going to say the big benefit also to a high pressure spray like this is that a pump station is versatile in that it can provide water or mist to several different zones. So we can go up to 4 zones. And those zones can have independent demands. So let's say you have a rooftop with several air handlers. You could have that split up 80 high pressure spray, 1 pump station to 4 air handlers. And so that's considerable cost savings, saves on so equipment, maintenance, and complexity. We can also do stages. So we can either do zones or stages, and basically a stage is within one zone, you can have multiple stages of on-off functionality. So that's your modulation ability. I get asked a lot about, what is a stage and what is a zone. Zone basically has its own set point, but a stage is going to be kind of underneath a zone as a on-off supply of water to the nozzles. So the modulation ability in a high pressure spray, and this is across manufacturers, is going to be basically the size of your nozzle rack that's connected to one of these valves. So these solenoid valves that control the water going to a nozzle rack. You can't turn off and on individual nozzles. So you could have a nozzle rack that's basically the size of your minimum pump output, and that would be your lowest point of modulation. And then you have a stage maybe that's twice that size, and then a stage that's 3 times that size. It's kind of project independent. And that's how you build your ability to modulate. And then you can also cycle these stages on and off. So when you get to the capacities that these are run at, and then you're if you're turning a stage on and turning a stage off, and that's providing moisture to the space has a large volume of air. It really works out that you can keep pretty close control without having the need to modulate the output like you would an electric humidifier. So just a little bit of difference in the way they operate. So basically our design has a pump. You can see that in the lower left. There's a pump and then a valve panel. So that's a path of the water through the nozzles and then back to a drain on the unit. And so this is typical installation options. You'd have inside a duct or an air handler, and you'd be spraying upstream, so into the airflow. That's going to give you your most efficient absorption. And then you're going to have a mist eliminator downstream of that. The mist eliminator is there to protect any equipment downstream and to provide a point of drain. It's not going to be always wet. If you're not running the humidifier, it's going to dry out. It's not, there's no basin for water there. It's just so you don't have carryover. And so that's part of the induct or in the air handler package. I get asked, what's the size of the section in an air handler? Typically 5 feet is good for access to the nozzles, and putting in the mist eliminator downstream and having some space for the mist to absorb. And the big benefit to using 1,000 psi in our high pressure is that we're going to create a really fine mist, so it's going to have that much more surface area, so it's going to absorb that much faster. Going within space is another option for distribution, and that works really well for like large like warehouses, print shops, really high ceilings, 30 feet plus. You're just making a little mist in the space. It gets there's a large volume of air. That air has a lot of energy in it, and it absorbs the moisture. So you're not like dripping or anything like that. I have a couple pictures I can show. In the case where you are putting the mist into space and you don't have all the high ceilings, we can pair that up with a fan and help distribute the mist without dripping or anything like that. So there's definitely multiple options there for in-space distribution. For in-space distribution, we can take our valve panel and put that outside of the humidifier, so that can save on installation costs as well. That's unique to our design, is to have this remote valve panel. It helps with some water hammer issues with running really long supply lines from the pump station, and it helps with cost perspective. So you can have one supply line from the pump station go up to a ceiling and then run everything out in like a star pattern. Makes a lot of sense from an installation perspective. The pump itself is available as a brass pump. So the brass pump is a lower cost, but still capable of the same amount of output. And then we can pair that up with a VFD as well to lower the minimum output and to make it a little ability to modulate or have more modulating stages on there. And then we have a oil-free stainless steel pump that's has longer intervals between service. I believe it's like 8,000 hours between service versus the maybe 3,000 hours with the brass pump. Service is different, but still, it's two options there. And then we have the RO water that pairs up with it, so works really well. If there's anything I wanted to add, I just have a picture. Let's see if this will play. So this is an example. It's hard to get a lot of pictures of these working inside air handlers, but inside space is not so bad. So this is a printing facility where we've installed high pressure spray, and to give you an idea of just what it looks like when you have a call for humidity, and it's just a little bit of mist coming out of nozzles. The nozzles aren't above any equipment or anything, in case there was a leak or something in the plumbing. Just something like that is adding enough moisture to keep their indoor relative humidity, and they're overcoming the cooling effect. This is in Wisconsin, so they're just using gas heat or some other kind of heat to overcome that cooling effect. All right, so moving on from high pressure spray, evaporative media is kind of a more simple approach to this whole process. Basically, you're just passing water over the media. But what you typically have to worry about with this process is your pressure drop of your media, the carryover, so you don't want to have mist coming off the media, and hygiene. So, that's obviously why it's not allowed in hospitals. We do have some measures to, make sure that's not an issue. So our design is basically custom built. We don't have set sizes. So we custom build this to your duct or your air handler size. And we integrate that with some as a standard silver ion treatment for the water. So it's passed over a microbial filter. And then we're also can do UV as an option. And so this can be made with a basin and a drain. So you're recirculating your water, and that's going to be more efficient from a water perspective, or it can be made as a single pass. So then all water is going down the drain. The reason why we make this all custom fit is that, for example, our competition may have set sizes. They're not going to have the same surface area. So we're going to have less pressure drop than if you're using blanking plates. It's not going to be required with our design. And huge benefit of this is that you don't need RO systems, so that's a less maintenance on an additional piece of equipment. You don't need to have that equipment. You can pass just tap water over the media. You can use RO water, but it's not required. And as far as pressure drops, we have several different thicknesses we can use for this. So we do have the pressure drop information, but this just gives you an idea depending on your what you're going to have as far as the thickness of the media. I will note that the droplet separator there, that's that lowest line on the left, that's what's going to be used with our high pressure spray. So that's also going to have the lowest pressure drop with a high pressure spray system. As far as service, it's fairly easy, no tools involved to remove a panel and then replace it. You do have to replace them. It's pretty rare. Most of these, so the evaporative media itself can probably last 5 to 10 years, depending on usage. Eventually, you will get scale that's going to form in the media, and that will you will need to change it out. Won't be as efficient. All right. And as far as the controller, these are all backnet available with backnet and everything like that, and connectivity. And we also do this with a fan in itself. This is unique pretty much to data center customers, have been our sole customer for the SKVF in-space adiabatic cooling. And the reason is it's just a perfect adiabatic cooler for individual data halls, certain types of data centers. So this has been a real high volume unit for us and really easy to service. And the capacities are standard. So it's we go up to 5,000 CFM on our units, and depending on what your conditions are in the space, that's what your capacity is going to be. All right, and here's just an example of one installed in a data center. And then basically what we're doing is the modulation's done with the fan, ECM fan, and the media then is wetted depending on how much moisture you want to provide or how much cooling you want to provide. So it can be controlled on temperature or it can be controlled on relative humidity. All right, so that's my adiabatic humidification. If there's any questions, I know I maybe went a little over, but hopefully we have some time.